Okay, let's begin. LOS A, B, and C. We're going to do it all in one run. Compare, contrast, and explain. So let's run through the LOSs here. Compare and contrast probability samples with non-probability samples and discuss applications of each to an investment problem. In doing so, we are pretty much going to cover LOS B, which is explain sampling error. And then finally C, compare and contrast simple random, stratified random, cluster, convenience, and judgmental sampling, which are different kinds of probability and non-probability samples. So they all flow into each other. So to understand what we're doing when we say sampling, imagine that we have a population and the population is quite large. We could never really discover the true parameters of the population by sampling or by observing all of the items in a population. We'll take a sample, and a sample is a method of obtaining information about a population's parameters, its mean and its standard deviation, through sample statistics. So these are our estimates of what the population parameters would be. Let's look at probability sampling. Here, every member of a population has an equal chance, that's important, an equal chance of being selected. Therefore, samples will be more representative of the population. I want to take a minute on this. When we get to non-probability sampling, we're not saying that the samples will not be representative. They have the potential to be representative of the population. It's just that with probability sampling, they will be more representative of the population. Simple random sampling, a subset of a larger population, such that each element has an equal probability of being selected. So let's say that we have a population of 500 items that we could look at. It's too many to look at. We only have time to look at 50 of those items. We'll use a random number generator to select 50 numbers between 1 and 100. We'll list all of these items in a spreadsheet down a row, 1 to 500. And this random number generator will tell us which rows will be our sample of 50, and we'll end up with a sample size n equals 50. It's easy to see that each stock has a 1/500th probability of being selected, and this is useful when data are homogeneous. So let me give you a real-world example. Let's say that you're investigating a mortgage-backed security and you're looking at the collateral. Well, a mortgage-backed security is made up of thousands of mortgages. You're not going to look at every single one. So you may decide, well, you know what, let's do a sample of 100. So you use a random number generator. You'll have all of the particular mortgages backing the mortgage-backed securities, and the random number generator will just grab mortgages at random, give you a sample of 100. Now you can conduct your analysis on the sample of 100 in terms of default rates, in terms of the average age of the mortgage, in terms of prepayment rates, etc. Next, we have systematic sampling. When the population is too large to code, we'll select every kth element until the desired sample size is reached. And again, with mortgage-backed securities, simply because there are thousands of mortgages backing any one single issue of a mortgage-backed security, it might be enough to say, listen, there's no logical ordering to how a mortgage enters a mortgage-backed securities. They're already randomly listed in the order that I get them. Why not just take every 20th one? It would be the same as generating random numbers and selecting something. You could just take every 10th or 15th one. When auditors audit a company in terms of its accounts receivable, if there are hundreds and hundreds of accounts receivable, there's no time to actually check each and every one. They'll say, well, out of the 350 accounts receivable, a subsample of 35 is good enough, so we'll take every 10th receivable and create our sample from that. Stratified random sampling. Population is subdivided into subpopulations based on one or more classifications, and then simple random samples are then drawn from each of the subpopulations, and they could be done with either simple random sampling or systematic sampling within each subpopulation. Each sample is then pooled to form the main sample. So all of these subsamples get pooled into the main sample itself. The main sample is certain to include items from each of the subpopulation in proportion to the size of those subpopulations. So each subsample is proportionate to the size of its subpopulation, guarantees that the population subdivisions are represented in the sample. so that your statistics will be more precise. So if we were sampling a population, for example, we might divide it broadly along male and female. And then we might divide it between under a certain age and over a certain age. And within the certain ages, we might divide it by income as well, so that we have a good representation of the entire population. All right, we're going to do a walkthrough of example 1 here in a moment, which uses stratified sampling with a bond index to give you a good example of what that looks like. But before we do that, let's introduce the notion of sampling error, because that is LOSB. And we'll slide it right in here. Now that we've seen a number of sampling techniques, let's just remind ourselves, sample statistics are estimates of population parameters. They are not exact, and they are subject to error. And that error is called a sampling error. And a definition of sampling error is the difference between the observed values of a statistic and a population parameter as a result of using just a subset of the population. So let's imagine that we have a population and we take a sample, and let's say the sample size is 50. We can calculate a mean of that sample. If we take another sample of 50 and calculate the mean, these will be different. They'll both be estimates of what the true population mean is, but they will be different. If we did it again, take another sample of 50, calculate a mean, it will also be different. So you can conceive of the mean of the sample being a random variable. If it's a random variable, it will have a distribution. So if we took all these means and drew a histogram, we would get something that looked like this over lots of different samples. We would get a normal or approximately normal distribution. The standard deviation of this distribution is called the standard error. And the standard error is a measure of precision of our estimate. The standard error is the standard deviation of the sample we used divided by the square root of n. So for x1, for example, if we took one sample, we would take the standard deviation of that sample divided by root n, and that would be the precision that we can attach to our estimate. So while S, which is standard deviation, is a measure of dispersion within a sample, the standard error is a measure of precision of the sample means. So these are all sample means. Once we plot these sample means, we have a distribution of sample means, and this distribution is called the sampling distribution of the sample means. A little look ahead to the central limit theorem, because we'll look at this in a little bit slower detail. But this is what the standard error is. It is a measure of the sampling error, a measure of the precision by which our estimate is close to the population parameter. All right, now that we've got sampling error out of the way, let's have a look at stratified sampling using a bond index. Example 1, bond indexes and stratified sampling. And just to sort of give you a high-level view here, if you were going to replicate a stock index, like the FTSE 100, there are only 100 stocks. Even the S&P 500, there are only 500 stocks. But bond indexes usually have thousands of bonds, so that if you were going to replicate a bond index to make an investment vehicle, that would be very challenging to do. So typically, you use a sampling technique to create a representative sample of the index. Well, the best way to do that is with stratified sampling. Suppose you are the manager of a portfolio of bonds indexed to the Bloomberg Barclays U.S. Government Credit Index, meaning that the portfolio returns should be similar to those of the index. You are exploring several approaches to indexing, including a stratified sampling approach. You first distinguish among agency bonds, U.S. Treasury bonds, and investment-grade corporate bonds. So right away we have 3 classifications. For each of these 3 groups, you define 10 maturity intervals. And it gives 1 to 2, 2 to 3, on we go, 20 to 30. There's 10 maturity intervals in the 3 groups, so we're all of a sudden we have 30 sub-portfolios. And also separate the bonds with coupons of 6% or less from the bonds with coupons of more than 6%. So in these 30 sub-portfolios, we further subdivide them into coupons greater than or less than 6%, so we'll end up with 60 sub-portfolios. Question number 1 asks that. How many cells or strata does this sampling plan entail? We saw how to do this in a previous reading when we had principles of counting. We have 3 classifications. Within each classification, there are 10 divisions in terms of maturity intervals. Within each maturity intervals, there's 2 more divisions in terms of coupon. So we just multiply 3 times 10 times 2. That's exactly what we do here. 3 times 10 times 2, 60 different strata or cells. Which we need to answer too. If you use this sampling plan, what is the minimum number of issues the indexed portfolio can have? Well, we would sample from each subpopulation. The minimum number that we can sample is 1, so the minimum number of bonds that our portfolio will have will be 60. At least 60 issues. Suppose that in selecting among the securities that qualify for selection within each cell, you apply criterion concerning the liquidity of the securities market. Is the sample obtained random? Explain your answer. Well, if we were going to select based on liquidity, we would then further have to subdivide each of those populations, each of those subpopulations by liquidity and sample in each one to be representative. But if we just say, okay, well, here's subpopulation 1, let's exclude those bonds that are not liquid. Well, suddenly you're not random sampling within that subpopulation. You're actually using a different sampling technique because you are purposely eliminating some. So there are some that do not have an equal probability of being chosen. Is this sample obtained random? No, it is not. That's example 1. Next, we have cluster sampling. The population is divided into clusters, each of which is a mini representation of the population. So you'll have a population, and rather than sample from this population, what you will do is you will divide this population into a number of clusters first, and then you will sample from the cluster. You may take a whole cluster, which is a mini representation of the whole population. Certain clusters are then selected as a whole using simple random sampling. So we might say, okay, well, we've divided the population into 20 clusters. Let's use a random number generator to generate 3 numbers. It might say 3, 9, and 18. We'll take cluster 3, cluster 9, and cluster 18, put them together to form our sample. That is called one-stage cluster sampling. So if instead, here's our population again, and we'll just divide it into just a few clusters like this. And let's say that we decided, we took random numbers. We took number 1, number 5, and number 7. And we took those and formed a sample. If instead of doing that, we just sampled within each cluster, and then took those samples and created a sample, that is called two-stage cluster sampling. Subsamples are selected from each cluster as opposed to each cluster as a whole. Cluster sampling usually results in the lowest precision, since a cluster may not be representative of the population, but it does have the benefit of being both cost and time efficient. And the reading gives this really nice exhibit. I thought I'd replicate it here, which really lays out graphically, or pictorially, I should say, the difference between the 4. So simple random sampling, we can see that we're going to grab 5 observations at random. We had a random number generator, and it generated numbers that ended up choosing those observations. For systematic sampling, notice that it is an even space, that our observations are evenly spaced out. It's every third observation is what we're going to take. For stratified sampling, we first divide the sample into 2 subpopulations. Whatever they happen to be, we divide them on whatever characteristic there is. And then we have a random sample on this side, and we have a random sample on that side. Or you could divide them into subsamples, and if they're fairly equal, you still could use systematic sampling on each side. Typically, you'll just use the simple random sampling for each of the strata. And then cluster sampling. Here, what we do is we try to create clusters that have equal representation of all of the characteristics within a data set, and we create a whole bunch of different clusters. And then we'll just say, okay, well, let's just take this cluster and this cluster. There's our sample. And that is cluster sampling. Or what you can do is within each cluster say, well, let's take this. In this cluster, you say, take this one. Over here, we'll take these 2, and these will then be our sample. This is single-stage cluster sampling, and this is two-stage cluster sampling. All right, now we'll look at non-probability sampling. Here we're looking at convenience sampling and judgmental sampling. Non-probability sampling depends on factors such as judgment or convenience, and when we say convenience, in terms of access to data, that getting this data set's just convenient, so I'll use this one. The risk in using non-probability samples is that they may be non-representative. And if they are representative, they're not as representative as probability sampling techniques would be. Convenience sampling, done a lot in academics, by the way, especially in psychology. Observations are selected that are easy to obtain or are accessible. I shouldn't say just in psychology. In experimental economics, it's used a lot as well. Not necessarily representative, but low cost. So a good example is an economics professor who has to publish a paper, wants to run an experiment to see how people make decisions, will use students in their class. Psychology does that a lot as well. They use students at a Midwestern university of average size, and that's everybody reading that knows, well, that's not a representative sample. That is clearly a convenience sample. You're just using what's available to you. Judgmental sampling, select observations based on experience and knowledge, and this has the potential to be better representative because we would think that the researcher probably has a better idea of what is representative. Useful when there is a time constraint and or the specialty of the researcher would result in better representation. We can think of auditing in this particular case where an auditor would, is not going to go through every single account, but has a fairly good idea that, look, if these accounts are okay, then everything else would seem to be okay. There is some experience and knowledge that would then help make better samples based on the goal that needs to be achieved. Let's walk through 2, 3, and 4. All right, example 2, demonstrating the power of sampling. To demonstrate the power of sampling, we conduct 2 sampling experiments on a large data set. The full data set is the population, representing daily returns of the fictitious Euro-Asia-Africa Equity Index. This data set spans a 5-year period and consists of 1,258 observations of daily returns, a minimum value of -4.1, maximum value of 5. So big N, 1,258. First, we calculate the mean daily return of the equity index using the entire population. By taking the average of all the data points, the mean of the entire daily return series is 0.035%. So we know the population mean. So now we're going to go through a couple sampling techniques and see how close we get to that population mean. The sample size M is set to 5, 10, 20, 50, 100, 200, 500, and 1,000. So we're going to sample the 1,258 observations using samples of 5, 10, 20, all the way to 1,000. At each sample size, we run random sampling multiple times, 100 times, to collect 100 samples to compute mean absolute error. The aim is to compute and plot the mean error versus the sample size. For a given sample size M, we use the following procedure to compute mean absolute error in order to measure sampling error. Randomly draw M observations from the entire daily return series to form a sample. So if it were 5, we take 5. Compute the mean of this sample. Compute the absolute error, the difference between the mean on this sample and the 0.035 that we know is the true mean. Compute the absolute error, the difference between the sample's mean and the population mean. Because we treat the whole 5-year daily return series as a population, the population mean is 0.035% as we computed in solution 1. We repeat the previous 3 steps 100 times to collect 100 samples of the same size M and compute the absolute error of each sample. Then we compute the mean of the 100 absolute errors as the mean absolute error for sample size M. So it's not that we just take one sample of 5 and look at the difference between our sample and the population. We do it 100 times, take the average of the averages of those 100, and then compare it with the population. By applying this procedure, we compute mean absolute errors for 8 different sample sizes. Exhibit 2 summarizes the results. This is the mean absolute error, 0.297. Look what happens when we get to 1,000. The sampling error really decreases. So this is an important observation. As N increases, the sampling error decreases. Mean absolute errors are plotted against sample size in Exhibit 3. Here we go. So how big do we really need to go? Well, we can see that we get a lot of precision really quickly, but as soon as we get to about 200, after 200, improvements come really slow, and then after 500, it hardly seems worth going to 1,000 in terms of the extra precision that you would gain. But ramping up very quickly to about 200, look at this significant drop down here. Mean absolute errors are plotted against sample size in Exhibit 3. The plot shows that the error quickly shrinks as the sample size increases. It also indicates that a minimum sample size is needed to limit sample error and achieve a certain level of accuracy. After a certain size, however, here it's saying 2 to 400, there's little incremental benefit from adding more observations. Second experiment, stratified random sampling. So we did the same thing again, except now we did stratified. We now conduct stratified random sampling by dividing the daily returns into groups by year. The sample size M is again set to 5, 10, all the way to 1,000. At each sample size, we run random sampling multiple times to collect 100 samples. We follow the same steps as before, except for the first step. Rather than running a simple random sampling, we conduct stratified random sampling, that is, randomly selecting subsamples of equal numbers of daily return groups by year to generate the full sample. So basically how they're doing it here is, for the first size, 5, there are 5 years here. So they're going to segment these 1,258 observations by year, by 5 years. Then to get a sample of 5, they will take 1 observation from each of the 5 years. To get a sample of 10, they would take 2 observations from each of the 5 years, and so on, so that their sample size is still the same thing. So we know what's going on. Let's look at the results. Again, look at the drop in the error rate, or the mean absolute error, and the increase in precision. And we see the same type of benefit going on here. A lot of benefit up to 200, then it really starts to taper off. After about 500, we don't get that much more precision. Let's see if we can get to the next example. This is just a couple of questions here. An analyst is studying research and development spending by pharmaceutical companies around the world. She considers 3 sampling methods for understanding a company's level of R&D. Method 1 is to simply use all the data available to her from an internal database that she and her colleagues built while researching several dozen representative stocks in the sector. Method 2 involves relying on a commercial database provided by a data vendor. She would select every 5th pharmaceutical company on the list to pull the data. Method 3 is to first divide pharmaceutical companies into the commercial database into 3 groups according to the region where a company is headquartered, and then randomly select a subsample of companies from each group, with the sample size proportional to the size of its associated group in order to form a complete sample. Method 1 is an example of simple random sampling, stratified, or convenience sampling. Method 1, use all the data available to her from an internal database that she and her colleagues built. Well, it's already available to her, and her colleagues built it. It sounds like it's just kind of right there. That sounds like a convenience sample to me, right? So number 1 would be C. Method 2 is an example of, let's remind ourselves here, relying on a commercial database. Select every 5th pharmaceutical company. That sounds like systematic, right? There it is right there, B, systematic. And method 3 was stratified. We can see that we broke it down into different regions. And then from regions, we broke it down into, we broke it down to the regions and then selected based on proportional size. So that is not simple random sampling, that is B, stratified random sampling. And let's see, we can get number 4, 2, 3, 4, yes. Calculating Sharpe ratios, 1 or 2 years of quarterly data. Analysts often use the Sharpe ratio to evaluate the performance of a managed portfolio. The Sharpe ratio is the average return in excess of the risk-free rate divided by the standard deviation of returns. If you've started with the Quant section and you're saying, wait a minute, we seem to be going over these things really fast, Sharpe ratios, bond indexes, don't worry, you will see it all through level 1. We're just using examples. You will see the Sharpe ratio. You're not being shortchanged by not having a longer discussion about it. You will see it again later. It's just telling you exactly what the formula is. It's the average return in excess of the risk-free rate of your portfolio divided by the standard deviation. This ratio measures the return of a fund or a security over and above the risk-free rate earned per unit of standard deviation of return. To compute the Sharpe ratio, suppose that an analyst collects 8 quarterly excess returns. During the first year, the investment manager of the portfolio followed a low-risk strategy, and during the second year, the manager followed a high-risk strategy. For each of these years, the analyst also tracks the quarterly excess returns of some benchmark against which the manager will be evaluated. For each of the 2 years, the Sharpe ratio for the benchmark is 0.21. Exhibit 7 gives the calculation of the Sharpe ratio for the portfolio. And in asset management, your Sharpe ratio is the measure of how much return you can earn per unit of risk that you're taking on. Having a high Sharpe ratio is a good thing. So here is our data, quarter 1 through 4. We have our quarterly average, 1%, versus, and here's year 2, 4%. Let's continue on. Quarterly standard deviation, 4.62, 18.48. So Sharpe ratio is 0.22. 1 divided by 4.62 and 4 divided by 18.48. If you calculate the Sharpe ratio for year 1 and year 2, you will get 0.22, the same in each year. The benchmark was 0.21. This manager has 0.22. For the first year, during which a manager followed a low-risk strategy, the average quarterly return in excess of the risk-free rate was 1%. That's the average. With a standard deviation of 4.62, Sharpe ratio was 0.22. The second year's results mirror the first year, except for the higher average return and volatility. Sharpe ratio for the second year is still 0.22. The Sharpe ratio for the benchmark is 0.21 during the first and second years. Because larger Sharpe ratios are better than smaller ones, the manager appears to have outperformed the benchmark. Now, suppose the analyst believes a larger sample to be superior to a smaller one. She thus decides to pool the 2 years together and calculate a Sharpe ratio based on 8 quarterly observations. The average quarterly excess return for the 2 years is the average of each year's average excess return for the 2-year period. The average excess return is 2.5% per quarter. Standard deviation for all 8 quarters measured from the sample mean of 2.5% is 12.57%, and we would end up with a Sharpe ratio of 0.199. Sharpe ratio for the benchmark remains at 0.21. Thus, when returns for the 2-year period are pooled, the manager appears to have provided less return per unit of risk than the benchmark, and less when compared with the separate yearly results. All from sampling a different way, we get a different result. If we sampled each year and calculated a Sharpe ratio for each year, we outperformed the benchmark in both years. But when you pool them all together and you say, well, let's do a Sharpe ratio over a 2-year period, we underperform. The problem with using 8 quarters of return data is that the analyst has violated the assumption that the sampled returns come from the same population. As a result of the change in the manager's investment strategy, returns in year 2 followed a different distribution than returns in year 1. Clearly, during year 1, returns were generated by an underlying population with lower mean and variance than the population of the second year. Combining the results for the first and second year yielded a sample that was representative of no population. Because the larger sample did not satisfy model assumptions, any conclusion the analyst reached based on the larger samples are incorrect. I don't think we have to keep reading here. So there is some thinking that we have to do when we sample from a population, is we first have to ask ourselves, well, hang on now. The population that we defined, is it a single population, or have we mixed a couple of populations in there? Are we sampling from multiple populations? When you get to level 2 and you look at time series analysis, that becomes important, that the longer the time series you're looking at, the higher the probability that you have separate regimes going on within those time series. Periods of high volatility or low volatility, periods of high inflation or low inflation together all in one sample. So there is some thinking and some observing that you have to do to the data series first to make the assessment that you are sampling from one population. All right, we are now on LOSD and LOSE. LOSD is to explain the central limit theorem and its importance. And I've done it a couple of times, briefly. I've touched upon the central limit theorem, but we've never really done it fully. We're going to do it fully here. And E is calculate and interpret the standard error of the sample mean. And in doing this, I'm going to lay out the distinction, the difference between a standard deviation and a standard error. And that you cannot use the word standard deviation when you're talking about standard error, because they are different. And I'll point out the 2 big differences between them. Let's start with the central limit theorem. Let's say that we have a population, and I'm just going to say this population has 1,000 observations. And it is any distribution. That's why I drew it this way. I didn't want to draw it out and having any distributional properties. We don't know what it is. And it could be anything. But we do know that it has a mean. We can calculate a mean of that population. And it has a finite variance. And finite, we also mean it has a constant variance. All right, let's take a sample. And if we take a sample, let's make our sample size 30. We know if we took a sample, we could calculate the mean of that sample, and we can calculate the standard deviation of that sample. We've already done that. If we take another sample, we can do the same thing. All the way to n samples, n being 30 samples, 50 samples, 100 samples, all of size 30, we can calculate a mean and a standard deviation. The mean of x1 will not be the same as the mean of x2, will not be the same as the mean of x3. None of them will be exactly equal. They'll be close, but they won't be equal. So if there were 100 samples here and you looked at all those means, which one is the population mean? They're all somewhat different. Our best guess of what the population mean would be is to take all of these means and calculate the mean of those means, and that would be our best guess of mu. And that's what we do down here. We take all of these observations and we plot them in a histogram, and that histogram will draw out an approximately normal distribution. So there's the, pay attention to the yellow line, that's associated with n equals 30. This is a distribution of sample means. It's not a distribution of the population. I want you to forget about that right now. All we've done is taken a whole bunch of means and looked at the distribution of those means, no matter what the population looks like. If we do this and we plot the sample means in a histogram, we will get an approximately normal distribution. Beautiful. Another property of central limit theorem is this. If we increase the size of our sample from 30 to 100, look what happens to the distribution. Look at what happens to the tails of the distribution. Here is our best guess of what the population mean is. This is a measure of precision. Well, we just got a little bit more precise. Increase the sample size to 200, and look what happens. We get even more precise. And in fact, if we took a sample of 1,000, this is what our distribution would look like. It would just be one straight line. Because we're sampling the whole population now, there would be no difference between the sample mean and the population mean. This is an important statement I'm making here. As n increases, the sampling error decreases. How do we measure sampling error? By something called the standard error. And what we do is we take the standard deviation of the sample we have and we divide it by the square root of n. And that's really just saying, listen, take the variance and divide it by n. Right? It's just sort of an average variance per unit, or an average the average variance per unit, you can call it. So if we want standard deviation, we know that it's s, and we just take the square root of the denominator as well. So there it is, s over root n. That is called a standard error. It is not called a standard deviation. I've heard it referred to as the standard deviation of the sample means. And while you could say, okay, I get what you're saying, it's technically incorrect. Let's look over here for an explanation of why it's incorrect. There are two explanations I'm going to give you. Number one, if we don't know the population variance, we'll just use the sample standard deviation. There's our standard error. If we know the population variance, we can use the population standard deviation and come up with our standard error as well. Standard deviation does not equal standard error. Standard deviation is a measure of dispersion from the mean. It is a way that we describe the distribution of our data. A standard error is a sampling error. It is not measuring dispersion from the mean. It is measuring the precision of our estimate. And we use it for data inference. The other reason why it is not considered a standard deviation is this. We went from n equals 30, n equals 100, n equals 200. Our standard error will decrease. However, if we were sampling a population and we went from a sample of 30 to a sample of 100 to a sample of 200, our measure of standard deviation would pretty much be the same. Constant. Standard deviations are constant and finite, whereas standard errors will shrink with an increasing n. It is a function of the size of the sample, whereas a standard deviation is not a function of the size of the sample. So it is appropriate to refer to the dispersion in the distribution of the sampling means as the standard error and not the standard deviation. All right, great. I've said all that. Why do we care about this? Why have we done all of this? Is because we want to say something about the population mean, but all we have is a sample statistic. What can we say about the population mean given that we have a sample statistic? We can say something close. How close? This close. That allows us to test how sure we are that our estimate is close to the population statistic, whatever it happens to be. So we can construct intervals in which we feel the true population mean would lie. We can construct things like 90% confidence intervals or 95% confidence intervals. We'd need our measure of precision to do that. But we can then say we are not entirely sure what the population mean is, but we are 95% confident it lies between this number and that number. And of course, the larger our n is, the tighter that interval is for the same level of confidence. So we're going to see confidence intervals later in this reading, but to understand confidence intervals, we have to understand that we need to work with a measure of precision, not a measure of dispersion, which is why we will not work with standard deviation in constructing confidence intervals. We will work with standard error. Okay, we're going to move on now to different methods of sampling that fall under the umbrella of resampling. And we use this when we have a particular problem. And our problem is there exists a population out there, but we know nothing about it. All we have is a sample. What can we do with this one sample? And what we're going to do is resample from the sample. So let's dive in here. Resampling is repeatedly drawing samples from an original data sample. Notice we're not drawing samples from a population. We're drawing samples from an original data sample in order to estimate population parameters. The first one we'll look at is the bootstrap method. And here you're going to use computer simulation because you have to observe values one at a time. You can't just take a sample and look at it. It's one at a time. So it can get really tedious. So there is some population that exists, some unknown distribution. I've drawn a little wall here and to show that, all we have is a sample size of 30, and that's all we have. We can't see what's on the other side here. This is all we have. What can we do with this? We'd use a system called resampling. And we'll create maybe 1,000 samples from this one sample. And here's how we do it. We only have 30. All of these samples will have an n of 30 as well. So you're probably thinking, how can you have a whole bunch of different samples of n equals 30 when the original sample is only 30? Here's how it's done. Draw one observation from this sample, record it, replace it. Draw another one from this sample, record it, replace it. What you will have in each of these samples is sometimes you'll have the same observation several times, but each of these samples will be different, will be somewhat different from each other. And you will do this n times, here n being 1,000 times. So rather than estimate the distribution, this method creates the distribution. So we don't know what the population distribution looks like, but from this sample and from all of these, we can create what a distribution would look like that did produce this sample. We can also find the standard error of an estimator even when no analytical formula is available. So we don't have to find a mean. We can find, for example, the median, and we can find a standard error for the median, which from an analytical perspective, there is no formulation for finding the standard error of a median. So here's what we do. These thetas represent, if you have B1 all the way to B1000, theta with a bar on top is